Find the critical numbers of the function f of x equals 3x to the fifth plus 15x to the fourth minus 25x cubed plus 4, and classify them using a graph. And actually, I think I will classify them analytically because I think that's a more precise measure anyway. So it doesn't matter. You could do either way. Starting off, we need to find the critical numbers. Now, the critical numbers are going to be any place where a function's first derivative is equal to 0 or the first derivative is undefined. Now, this is a polynomial function, which is a smooth, continuous curve. So there's not going to be any places where the first derivative is undefined. So we just need to work on where this first derivative is 0. So the first derivative is 0. Well, let's get the derivative to begin with. So this would be 15x to the fourth using the power rule plus 90x to the third minus 75x squared. And it certainly looks like I have some things I could pull out as common factors, which is great. It's probably going to make the next steps a little bit easier because I do now need to set this equal to 0 and solve. So the common factor here looks like it is 15x squared. So that would leave me x squared plus 4x minus 3. And let's see if this factors. I believe it will. If I have 3 and 1 here and both values are negative. Oh, nope, that's not going to work. Find the critical numbers of the function f of x equals 3x to the fifth plus 15x to the fourth minus 25x cubed plus 4, and classify them using a graph. Okay, well, critical numbers, what we know about critical numbers is that they occur whenever the first derivative of a function is equal to 0 or the first derivative is undefined. Now, this polynomial function, and all polynomial functions that is, are smooth continuous curves. So they don't have any places where the first derivative would be undefined. So we're not going to worry about that situation, but we are going to worry about where its first derivative is 0. And we'll begin by getting the first derivative itself. So let's see, 3 times 5 is 15x to the fourth using the power rule. And plus 4 times 15, I believe is 60. Let me just double check. Don't want to make an arithmetic error. All right, yep, that is 60. So plus 60x cubed minus 75x squared. All right, and then the derivative of 4 is, of course, 0. Now, I want to know where this is equal to 0. So I need to set this equal to 0 and solve. And one thing that I notice is it looks like 15x squared is a common factor here, which would leave me x squared in the first term, then 60 over 15 I think is 4. I think that's what, yeah, that's 4. So plus 4x and 75. That's 5. Okay, so minus 5, and then pulling out the x squared. All right, now these will factor. This would be 5, and this could be 1, and if the 5 is positive and the 1 is negative, that would add up to positive 4, but then multiply to negative 5. Great. So what that means is my critical numbers are these. X equals 0, coming from the x squared term. X equals negative 5, and x equals positive 1. So it looks like I have 3 here. Now, the next thing is to classify them. And it said to use a graph, but we can use a graph or we can do this analytically. And personally, I prefer using analytics here because it's a little more precise. Classifying them means determine if they are relative minimums or maximums or neither. Sometimes that could happen. In order to do that, I will take these critical numbers and put them on a number line. Make sure they're in order from least to greatest, so -5, 0, and 1. And then I'm going to pick some test values. So the test values I'll choose here just have to be on each interval. So how about -6, -1, and 0.5, and 2. All right. Now, what I'm doing is I am taking these test values and plugging them into the first derivative. And the reason is if say f of -6 results in a negative number, then that means my function is decreasing on that entire interval. So if I go from decreasing to increasing, then I know that I had a minimum there, and I can classify that number that way. So that's what I'm working toward here. So the next thing that I'm going to do is determine if the first derivative is positive or negative on each of these intervals. And I think the easiest way of doing that is, because I have so many values, just to use the table feature within the calculator. So 15x to the 4th plus 60x cubed minus 75x squared. And if I go to the table and start putting in these values that are of interest here, -6, -1, 0.5, and 2. All right, so f of -6 is a positive value. F of -1 is a negative value. F of 0.5 is also a negative value. And f of 2 is a positive value. So if the first derivative is positive, that means we are increasing on that interval. If it's negative, then we are decreasing. Then it's decreasing again here. And lastly, we are increasing. And what's important about that is if I go from an interval that's increasing to decreasing, then a critical value that occurs there has to be a maximum. So that classifies that. Now, if I go from decreasing and then start decreasing again, well, that's neither a minimum or a maximum, so that is neither. And if I go from decreasing and change to increasing, then that's a minimum. All right, so I have these now classified. So x equals -5 is a relative maximum. X equals 0 is neither. Neither a minimum or a maximum is what I mean there. And x equals 1 is a relative minimum. And if you want to see what the graph looks like, we already have it in the calculator, so we can just press graph. And the scale looks kind of crazy. But you can see here what happens. It comes down really far, turns back around, and then it has this peak, okay, but it sort of bounces back away. It's hard to tell from this graph. It's not the best, but I bet if you zoom in on there, it would make a little bit more sense. So if you did want to see why we end up with a neither here, you could look at the graph, but make sure you go and put the original function back in. So that would be 3x to the 5th plus 15x to the 4th minus 25x cubed plus 4. And when we graph now, oh, my scale's kind of crazy, but you can kind of see right in this region is where something's happening. So I tell you what, I'll just zoom in on that region. I'll do a zoom box. So a zoom box, you just kind of pick a rectangle that you want to particularly zoom in on so you can see a better picture of just that part. All right, so there you can see it. So here, the graph is coming down, and then it flattens out, but then it starts decreasing again. So it doesn't change to increasing. So that's why we have neither a maximum or a minimum.